welcome to the class. So in today's class, we'll be discussing physical quantities in physics. Assalamu alaikum everyone, welcome to the class. So in this class, we'll be studying the first chapter of physics. Uh, you can call it measurements or physical quantities. Both are names for this first chapter, or you can also call it length and time. So I'll just like to introduce myself first. My name is Harun Tariq, and I've been teaching for a good 7+ years now, Alhamdulillah. And I had really good grades in my O levels, A levels, and IGCSEs. And I basically had a most number of A grades in the category of Cambridge exams and O levels, IGCSE, and A levels. After that, I went to Australia to study software systems, and I came back and started teaching um, these subjects basically, Cambridge O and A levels / IGCSE as well. Okay, so let us get started with the first chapter of physics. So, measurements. So, we'll do the concepts first, and after that, we'll do past paper questions too. So, all physical quantities they have two parts. One of them is magnitude, and the second one is the unit as well. So, magnitude, what do we mean by magnitude? So, for example, I can say I want to walk 30 meters. So, this 30, the number that we have, this is our magnitude. This is our magnitude. And this m, meter in this case, this is my unit. Let's say I'm driving my car at 50 kilometers per hour. So this 50 that you see, this is my magnitude. Magnitude is basically the number, the size. And the unit in this case would be kilometers per hour. This is unit for speed basically. Not the SI unit. The SI unit is meters per second, but one of the units. Some physical quantities, they also have direction. We refer to them as vector quantities. Not all of them would have direction, but some can have direction and as well, and we can denote it by arrowheads like this. Now, in physics, we basically have 7 base quantities, but in our syllabus, we have 5 base quantities: mass, length, time, current, and temperature. These are the 5 physical quantities that we have in our syllabus. The SI unit for mass would be kg. For length, it would be meters. For time, the SI unit is seconds. For current, it would be amperes. And for temperature, it actually has 2 SI units. We generally use degree Celsius, but we can also have Kelvin, which is represented by uppercase K over here. Now, these 5 base quantities, or rather it's 7 in total, they derive other quantities as well. So, for example, the formula for speed, which we'll do in the next chapter, speed is equal to distance divided by time taken. Now, this distance is actually your length. This is your length, and we have a base quantity known as time as well. So you can see time is actually a base quantity. Distance or length is a base quantity as well. So we can derive other physical quantities by these 7 base quantities that we have. And the SI units are standardized units. Back in the day, we didn't have standardized units. So it caused all kinds of confusion throughout the world. We could have different units in different cities or different countries. So basically, what the scientists did was they had standardized units. So those units that we have would be true for everywhere in the world. Now, SI units are standardized units that we have. For example, for mass, we use kg, kilograms. For length, we use meters, and so on. Now, next up, you are expected to memorize a few prefixes. This table is examinable. Now, the value of tera is 10 raised to power 12, and we represent it by uppercase T. Giga 10 raised to power 9, mega 10 raised to power 6, kilo 10 raised to power 3, and you can see uppercase G for giga, uppercase m for mega, and lowercase k for kilo, not uppercase, lowercase. For milli, we have 10 raised to power minus 3 and lowercase m. Uh, Micro, 10 raised to power minus 6, and this is the symbol for micro. And for nano, 10 raised to power minus 9, and lowercase n is the symbol. Now, if I say, for example, 50 millimeters. So basically, in terms of meters, this would be 50 times milli is 10 raised to power 3. You can see over here. So 50 multiplied by 10 raised to power minus 3, and this would be in meters. So milli means 10 raised to power minus 3 basically, right? 10 raised to power minus 3. Okay, now you need to know these symbols as well. These are examinable, including the symbol for micro. The rest are like standard, not that hard to memorize. Okay, now physical quantities may or may not have a direction. The magnitude, I have already stated that this is the size, the number. Scalar quantities are those quantities which have only magnitude. Unit exists for all the quantities, not all of them, but generally for almost all of them. Uh, the scalar quantities, they have only magnitude and no direction. Now, some of the scalar quantities that we have, you need to memorize these as well over time. It's easy to memorize when you read this again and again. When you do all these chapters over time, it's easy to memorize the scalar and vector quantities. Length is a scalar quantity. Volume is basically length times width times height. The three dimensions multiplied by each other. This is basically for cuboid. You can have cube as well. That would be length times length times length. And we have other formulas for other regular shapes. So all of these are lengths. So in three dimension, we have length in three dimension would be volume in 3D. So this is also a scalar quantity. It doesn't have any direction. Mass, no direction. We don't say my mass is 50 kg to the right or 50 kg towards north. So it doesn't have any direction. Speed is a scalar quantity as well. There are other physical quantities which are scalar, for example, energy, right? Or we can say distance as well. Length and distance are the same. So we have other scalar quantities as well. These are just a few examples. Now, next, vector quantities. These are those physical quantities which have a magnitude as well as direction. They have magnitude plus direction. When any physical quantity has magnitude is the size, of course, as well as direction, it would become a vector quantity. I'll just write a few examples on the previous slide. So for example, length of 50 meters, it can be other units, kilometers. Volume of, let's say, 20 cubic centimeter. Mass, let's say 15 kg, let's say. We don't have any directions, as you can see. Speed, traveling at, let's say, 30 meters per second. So we don't have any directions over here, right? These would be scalar quantities. Now, force, weight is also a force, and weight, for example, acts vertically downwards. It has a direction. Force will have a direction, as is being shown by this arrowhead as well. You see, this arrowhead basically shows the direction. So it would be vector quantity. Let's say my force is 50 newtons. Uppercase N is the unit for force newtons. So velocity, this would basically be speed with the direction, which we'll do in the next chapter. So let's say 50 meters per second towards north. This 50 is your magnitude. This meters per second is your unit. And this towards north is your direction. So when we add direction to speed, it becomes velocity. Displacement is basically length in a specific direction, distance traveled in a specific direction. So let's say 30 meters uh, towards east. So this towards east would be the direction, and 30 would be the magnitude. So acceleration, let's say 15 meter per second squared. This is the unit for acceleration. So acceleration can be positive, negative. Positive means forward, negative means opposite deceleration basically. So it can be positive or negative. The sign would actually tell us whether it is positive or negative. So whenever physical quantities have a direction, they would be known as vector quantities. Now, scalar, they have only magnitude and no direction. Both have units, of course. And vector quantities, they have direction as well as magnitude. Okay, now length measuring tools. Now, how do we measure lengths? We have multiple tools to measure lengths. One of those tools would be a ruler or a meter rule. So what we do over here is, you can see this is my starting point. This is my ending point. Now, if I do ending point minus starting point, basically 9 minus the starting point was 0, this gives me the length. Now, why do we always do final value minus initial value? Because we need to remove the zero error. There is no zero error over here, but sometimes the length can actually start from a value that is not 0. So let's say we have another object that starts from, let's say, 3 and ends at 11, let's say, right? So for this object, if I want to measure its length, its starting point is 3. This is the starting point, and its ending point is 11. So now this has zero error. So I need to remove the zero error. How do I remove the zero error? Just by doing the final value, which is 11, minus the initial value, which is 3. So this gives me 8 centimeters. So always avoid the zero error. This would be standardized for all the tools. Final minus initial would give us the actual value that avoids the zero error or that adjusts for the zero error. If our line maybe starts from before 0, let's say if the examiner asks you to find this line, we actually would need to add this value in that case, not subtract, right? But that is when we'll do past paper questions, maybe we can come across a question similar to this one. In that case, we actually add this particular value. So for example, we have those weighing scales. Sometimes they might start from, let's say, 3 kg, and if the weighing machine shows 83, it does not mean your actual mass. That is not actually the weight, it shows the mass. So it won't tell you that the mass is actually 83 kg. It would be 83 minus 3. You need to adjust for the extra 3 kg it showed initially before getting your mass, right? So we need to adjust for the zero error in both cases, positive or negative. Now, this meter rule, there are a few situations in which this is suitable. This is suitable for measuring straight objects, and the general range that we use it to measure would be starting from 10 centimeter. Generally it can measure lengths of less than 10 as well. It's not as if it can't measure it, but it's just that for less than 10 we have other tools which are more accurate than this. From 10 centimeters to 500 centimeters. So basically this is 0.1 meters, just converting it in meters to 5 meters. Okay, now so keep this range in mind. This is examinable, 0.1 meters to 5 meters. Now this is used to measure straight objects, of course. Now next up we have tape measure. Tape measure is used to measure curved objects. It's not as if it can't measure straight lengths. It can. It's just that meter rule is more appropriate for it. This is suitable for curved lengths. So for example, if we have a circle and we want to find its circumference, would actually be the perimeter. So the border that you see, this border, this circular length that you see. So for it, this tape measure would be more accurate or more suitable. So used for curved lengths, and this has a bigger range. It starts from 10 centimeters. It does not mean it can't measure less than 10 centimeters. It can. It's just that we have more accurate tools, other tools which are more appropriate for it. 10 centimeters to, you can say, even 10,000 centimeters. So you can say, so for example, 0.1 meter to 100 meters. So it's just that the tape should be long enough. You can have a 100-meter tape as well. It's just that the tape should be long enough. You can use this as well to measure curved lengths as well as to measure very long lengths. Next up, we also have a trundle wheel. It looks somewhat like this, and trundle wheel is basically used to measure curved lengths as well as straight lengths, and it is used to measure longer lengths. For example, we want to measure the length of, let's say, 2 kilometer road. Tape measure would not be that appropriate. So we can use the trundle wheel, or we can use other tools as well to measure longer lengths. But trundle wheel basically looks like this, and if it is digital, you just start the digital meter and you start moving this trundle wheel. This has a wheel, as you can see over here. When you move, the that counts into the length or the reading, and when you end, you can just have a look at the digital scale that gives you the final reading for the length. Now the next length measuring tool is the micrometer screw gauge. Now micrometer screw gauge is used to measure lengths of less than 1 centimeter. Less than 1 centimeter. You can see this is a very small length. Less than 1 centimeter. Also in terms of millimeters, basically 10 millimeters. Less than 10 millimeters. 10 meters or below. Now this would be the most accurate tool for it. So for example, if you have a ball bearing, we can put the ball bearing over here, and we want to measure its diameter, you can say, from this point to this point. If you want to measure this length, all these labeling that you see, this is just for concept, this is not examinable. So we can measure this diameter for this ball bearing, for example, through this tool known as micrometer screw gauge. And this is the most accurate tool in our syllabus. We have different length measuring tools, for example, the ruler, basically meter rule, tape measure. Vernier caliper was previously in the syllabus, not anymore. And we have a micrometer screw gauge as well. So this is the most accurate instrument, but the thing is, it only measures very small lengths. The smaller the lengths it measures, the greater the accuracy, of course. Now, how do we take the reading of the micrometer screw gauge? So for micrometer screw gauge, we have two parts. One is the main scale reading, and the second one is the thimble scale reading, or the rotating scale reading. So rotating scale, we call it thimble scale as well, fractional scale. There are multiple names for it. So the first thing that we do, this is the main scale, of course. This is your main scale, and this scale that you see, this is your thimble scale, or rotating scale. So the first thing that we do, wherever the main scale reading ends, that is the reading that we want. So over here, this is 0, so this would be 1, 2, 3, 4, and as you can see, we have 5. And this line at the bottom that you see, this is right between 0 and 1. So this would actually be 0.5. This would be 0.5. So the next line that you see over here, this is between 1 and 2, so this would be 1.5. So you can see we have a line over here which is after 5. So this would be 5.5. So this is where our main scale ends. So you can see we have this line that is after 5 basically. So the main scale ends at 5.5. So we take the last part of the main scale and we write it over here. So the main scale reading, the final reading is 5.5. Okay, now next we need to find the rotating scale. Now this horizontal line that you see, this line over here, this line is known as datum line. Datum line. Now wherever this datum line coincides with the thimble scale, that is the reading that we want. So if I make a horizontal line over here, this is coinciding with this particular line. So this is 25, next would be 26, 27, 28. So this is coinciding with the 28th line, as you can see. This is coinciding with the 28th line on the thimble scale. So for the rotating scale, what we do is we take this reading and we always divide it by 100, because 100 of these lines, see, 100 of these lines would be equal to 1 millimeter, and the readings that we are taking are in millimeters. For main scale, we got our reading in millimeters as well. So I just need 28 lines reading in terms of millimeters. So we always divide it by 100. 28 divided by 100. So this gives me 0.28, and this would be in millimeters as well. Always divide by 100. Now final reading would be your main scale plus rotating scale. So 5.5 plus 0.28. This should give me the answer 5.78. And this should be in millimeters. This is my final answer. 5.78 is my final reading. So this is how we find reading of a micrometer screw gauge. This is examinable. You need to know this. So if you want to take a screenshot, basically these are notes, or just pause the video and read over these notes. Next up, this is what a vernier caliper looks like. This is no longer examinable, but for just for concept sake, you can just briefly discuss it. This won't be examined anymore. So for vernier caliper, basically the suitable reading is 1 centimeter to 10 centimeters. If you remember, for meter rule and tape measure, I told you guys more than 10 centimeter. The range, of course, was a lot larger for tape measure as compared to meter rule. The reason being, meter rule, imagine we had a 100 meter meter rule. Where would we store it? Because it can't bend, it would just break. But tape measure, you can store a 100 meter tape measure in a very small container. So that is why the meter rules maximum reading is lesser as compared to tape measures. Over here, this is the range. For less than 1 centimeter, it was micrometer. 1 to 10 centimeter vernier caliper. More than 10 centimeter, either meter rule or tape measure, depending on whether it is straight or curved, and the range. So over here you see this part, the stem. This is used to measure depth. So depth would be this length over here. This is my depth. This can be measured through the vernier caliper. And these jaws that you see, basically, if we have a ball bearing, for example, and we want to find its diameter, or if you want to find the external diameter from here to here, external diameter of the glass, then we can use these jaws. And we also have these other jaws which are used to find inner length. So these jaws that you see, these are basically used to find the inner length. So for example, the length from the inner part of the glass from here to here, basically the inner part of the diameter of this glass, basically. Okay, now this is just a summary for meter rule tape measure. The range 10 centimeters to 500 centimeter. But you should know, for tape measure especially, it can measure up to, this is for tape measure only, up to 100 meters as well, depending on the size of the tape measure. The tape measure should be big enough. And for vernier caliper, 1 centimeter to 10 centimeters, micrometer screw gauge less than 1 centimeter. And the smallest length measuring tool is the micrometer screw gauge. So this would be the most accurate, most precise. Most precise. This gives you the reading to the closest degree or the closest unit, basically. This would be the most precise. The smaller the instrument, or the smallest the appropriate length it measures, the greater the precision of that particular tool. Next up, we want to find volume. Volume is length in 3 dimensions. So this is a cuboid. Volume of a cuboid would just be length times width times height. And all these lengths are straight. So to find volume of a cuboid, I just need a length measuring tool. So I just need a meter rule. So through a meter rule, I can actually find the volume of this particular cuboid. Just measure the length, the width, and the height, and put it in the formula. We get our answer. So what this tells us is, for regular shapes, if you want to find volume of regular shapes, what we need is length measuring tool. Length measuring tool. It's just that we should know the formula and the appropriate instrument. So for example, cube, length times length times length, just use a meter rule to find one of the lengths. All the lengths would be the same. Put it in the formula, you get your answer. Even if you have a sphere or a cuboid, these are regular shapes, and we can actually find the volume by just a length measuring tool. But sometimes we have irregular shape. So for example, let's say I have a stone, and the examiner asks, I can't recognize this the shape over here. This is neither a sphere nor a cylinder, cylindrical shape, cuboid, uh, cube, none of the regular shapes, right? So for irregular shapes, we use a method known as displacement of water. Irregular shapes, to find volume, we use a measuring cylinder. And the name of this process is basically displacement of water. This is your displacement of water method. So what we do over here is, we take a measuring cylinder, we pour some water inside it. The water should be enough to, so that this entire irregular object, for example this stone, can actually go inside, the entire stone can go inside the water. So the measuring cylinder should be big enough to contain this stone, of course, or this irregular shape, and the water inside it should be high enough for this entire irregular object to fully get submerged inside the water. That is a condition. So we take the initial reading with water inside the measuring cylinder but no stone inside it. So we call this reading V1. Then we put the stone inside the water. The condition is the stone should be fully submerged inside the water. So for example, if I had a bigger stone with a longer length, this will only give me the reading of the part, or the volume of the part which is submerged inside water. So this part would not be included in that. So that is why it should be fully submerged inside water. That gives us the accurate answer. So in our example, you can see stone is actually fully submerged in water. So this will give us the correct reading for volume. Now we take the second reading. This is the reading of water plus stone. We call it V2. Now we just need to do V2 minus V1, the final reading minus the initial reading. So my final reading in this case is 25 minus my initial reading with only water. This would give me 5 cubic centimeter. So this was water only, and this was water plus the irregular object, which in this case is the stone. So when I take this reading and I subtract this one, this removes the water part from it, and when this water part is removed, the only part that is left is the volume of the stone. So that would give us the final answer in this particular case. So final minus initial, basically. Okay. Now to measure volume through a measuring cylinder, there are a few concepts that you should know. In our syllabus, we only have concave meniscus. So you don't have to know convex meniscus. We don't have this in our syllabus. But just to be on the safe side, or just to know the concept, although this is not in your syllabus, you always take the reading at this central point, basically at the bottom of the meniscus. We will always take the reading at the bottom of the meniscus. Always bottom of meniscus. So if you give this reading, let's say this is 17 and this is 16. If you give your reading as 17, that would be marked incorrect. 16 is the actual answer. We always take this reading at the central point, so always at the bottom of the meniscus. In this case, we would have taken this reading top of the meniscus, but this is not in your syllabus, so ignore this part. This is just for concept. You will always say we always take the reading at the bottom of the meniscus, because we only have concave meniscus in our syllabus. Next, now in terms of volumes, we have three or four different measuring cylinders over here. Now the most accurate would be the smallest one, just like micrometer screw gauge was the most precise. So this will give us the best reading. This is the most accurate or precise, and this one is the biggest one, would be the least accurate. So whenever the examiner tells you uh, to find the most accurate volume, which measuring cylinder do we take? We always take the smallest measuring cylinder possible. Smallest measuring cylinder possible. is the best. That gives us the best answer. But we also need to look at the range it measures, right? So for example, I have a stone that has a volume of somewhere around 30 cubic centimeter. I don't know exact, but I just say it is in the ballpark of 30. But this smallest measuring cylinder, that this measuring cylinder's maximum limit is 20 cubic centimeter. Now, although this is the most accurate, but this is not suitable to measure this volume. So it has to be in this range. So the maximum limit should be in the range. Otherwise, we can't really use it. So the smallest measuring cylinder possible would be the best measuring cylinder for us to take the reading. But the thing is, it should at least its maximum range should be within the range of the volume that you are measuring for the irregular object. Okay, now next concept related to volume, we always take the reading at the bottom of the meniscus, of course. So that would be this particular reading that you see, this would be the correct answer. Bottom of the meniscus, and you can see we need to avoid parallax error. We need to avoid parallax error. Now, how do we avoid parallax error? Basically, you see, I need to take this reading. So my eye level should be level with this part of the scale. If it is level with it, it will give me the correct answer. But if you look at it from a different angle, for example, this angle, this gives me too low a reading. You can see this is smaller than the actual reading of 19.70. So this is inaccurate, incorrect. And if you look at this reading from this angle, let's say, it gives you too big an answer. So both these are parallax errors. So your eye should be level with the reading that you're taking. So we must always avoid the parallax error whenever we are taking the reading. It doesn't matter whether it is volume or anything else, a meter rule reading. We must avoid parallax error so that your eye is level with the reading. Basically, it always makes a perpendicular or 90-degree angle with the scale that we are measuring it with. So we have a 90-degree angle, you can see. So your eye should be level with the reading. Next, your measuring cylinder should always be like vertical, always arranged in a vertical format. Because for example, if we put it like this, which reading do we take for the volume? So do we take this reading or this reading? This second reading, this would be too low, this would be too high. The actual reading would be somewhere in between. So it should be always vertical like this. You need to place it vertical so that you can actually take the correct reading, basically this reading. So to measure volume, this is just common sense basically. The measuring cylinder should always be vertical. Okay, now next, volume of we sometimes need to measure volume of floating objects. We have already done irregular objects, but that was for sinking objects like stone. So what we did over there was we take measuring cylinder, we pour water in it, then we take that reading, we call it V1. We pour, or rather place the irregular object inside that measuring cylinder. We take the difference between the two readings. This second reading would be known as V2. We take the second reading and we subtract the initial reading from it, V2 minus V1 in this case, and that gives us just the volume of the irregular object. But sometimes the object doesn't sink. This is for sinking object, and I told you guys the entire object, irregular object, actually has to sink, or it should submerge inside water. Otherwise you get an incorrect answer. You do not get the actual answer or the actual volume in that case. So for irregular floating objects, we have a slightly different method. What we do is we take a sinker. This is usually a metal. We take water and we put a metal inside that water. So basically, sinker is just a tool or a metal that we use to sink that floating object, which you'll understand in a bit. So this will give me the reading of metal, which is the sinker. So I'll just write sinker, I guess, to avoid confusion. This would be water, volume of water plus sinker. Sinker is the metal that we are using over here. Next, we take out the sinker, we attach this sinker that we had to the floating object, for example a wooden cap or a wooden cork. So what we do is we have a wooden object, we attach this sinker, you can apply some glue, or you can maybe use a rubber band to attach it with it. The size of the rubber band should be thin so that it doesn't affect our reading too much. So what we need to do is we need to attach this sinker to the metal. Once it is attached, now we put both the sinker and the wooden object which was floating initially inside water. So now this would give me the reading of water plus sinker, which was the metal that we were using, and plus wood, the small piece of wood. So this would give me the combined reading of all these three. Now what I do is I call this reading, you can call this V2 and this one V1 as well. Over here I'm calling this V4 and this one as V3. This is V3 just for water plus sinker, and this is V4. So what I do is I just take V4 minus V3. That would give me the reading of just the wooden object, because you see this entire thing combined. This is water plus sinker plus wood. When I subtract this from it, the water part and the sinker part would be removed. These two would be removed, and when these two are removed, the only thing that is left is the volume of the wood. So this is for floating objects. This can come in your theory exam as well. So make sure you know this process. Another layman method, this is the actual method, but another layman method could be you take a stick, you have this measuring cylinder, you with help of the stick you can push this inwards, and make sure none of or very little of this wooden stick is inside water, because if this stick is inside water, then this will give you some reading of the tip, whichever part is inside water. We don't want it, we want an accurate reading. And you also need to make sure this entire wooden object is actually submerged inside water. So you apply a force from top with help of a stick, and make sure this entire object is inside water and none of or extremely little of the stick is inside water. And that is a method that you can use to measure volume of floating objects as well. But this is a layman method, this is not very accurate, because it requires a lot of focus, uh, and none of the stick to be inside water and all of the wooden object to be inside water. So that is not an easy thing to do. Okay, now next concept is related to time. So we can use stopwatches to measure time, and we also have human reaction time. So we need to human reaction time is just like this is natural for all the humans. uh, we take time in evaluating things and then implementing on them. So if I want to stop my stopwatch, first I'll observe. Let's say someone is running, and as soon as they hit the finish mark, I want to stop the stopwatch. I will first observe. It will take time for me to analyze the data, my brain to analyze the data, and it will take some time to implement that data and stop the stopwatch. So the time it takes for that to happen, this is known as the reaction time. So we need to limit the reaction time whenever we are taking the readings of a time or any other calculations. So for that, we actually use a concept known as multiple readings. So for example, the examiner asks you or someone asks you to find thickness of a sheet of paper. Now, thickness of a sheet of paper is extremely small, extremely small. So there is no length measuring tool. You might use a micrometer, but that won't give you an accurate answer, because this length is extremely small, thickness of a sheet of paper. So, what is the best strategy? Just take multiple papers, as the name suggests, multiple readings. You take, let's say, 100 papers all together, and you measure their length, all 100 combined. So, let's say I get 1.5 centimeters. This is for 100 pages combined, let's say. Now, to find the accurate answer, what I do is I just take 1.5 and divide by 100. That will give me the width or the thickness of just one sheet of paper. So this is the multiple readings concept. When we have readings which are extremely small, we take numerous or multiple readings together, and then we divide it by the number of readings that we took, basically averaging out, and that gives us the final answer. So over here on this slide, you can see we want to measure thickness of paper. So what we do is we can maybe take 250 sheets. You can take different, for example, 200, 150. So over here we are taking 250 sheets. We use a meter rule, vernier caliper, or micrometer, depending on how many sheets we took. You measure that, and we got 2.5 centimeters, and then you just divide it by the number of sheets that you took. So you can see over here, this is inches, 1 inch. So in inches, 1 divided by 250, and in centimeters, it was 2.5 centimeters divided by 250. That would give you the final answer. So this is the multiple readings concept. This multiple readings concept can also be implemented over here to measure period of a pendulum. So this pendulum, this is basically known as a bob. In this pendulum, basically it goes towards this side, and when it reaches its peak over here, then it comes back. So the time it takes for one complete swing, so from this side, from left to right, and then back from right to left, the time it takes for this entire journey, both of them combined, to and fro, this is known as one period. So let's say the examiner tells you to find time taken for one period, but humans, they have reaction time, so that won't give us a very accurate answer. To reduce the chances of human reaction time, what we do is we take multiple readings. So for example, I'll take the reading of, let's say, 20 oscillations. 20 oscillation, by oscillation I mean 20 full rounds to and fro. So let's say I take the reading of 20 full rounds, I measure that reading, and at the end, I just take that reading. Let's say I got X as my reading, X amount of seconds for 20 oscillations. Then I just divide it by 20. That gives me the reading of just one single period, one single oscillation. And that would be the most accurate way of doing this, because my human reaction time is now divided over 20 readings rather than just one reading. This is not me taking one oscillation, then stopping the stopwatch, then taking second oscillation, stopping the stopwatch, and then adding all of them together and dividing by 20. No, I just take the 20 oscillations combined once, and then I divide it by 20. That would divide my human reaction time uh, among among these 20 readings, and that would have little to no effect on my accuracy, or on my final answer, as in it would be a more accurate answer. So multiple readings can be practiced for this as well. Now, next up, the last concept, although this isn't examinable too much, but just for concept's sake, a lot of students get confused in accuracy and precision. So now, what do we mean by accuracy and precision? Now, accuracy basically means how close a measurement or an attempt is to the actual target value. So, for example, we have a dartboard. Now, so your accuracy would be you hitting this bullseye, basically this yellowish region. If your hits are on this yellow region, that means you are accurate. So this basically means how close your attempt is to the actual target. That is accuracy. Now, precision is slightly different, which we'll get to in a bit. So this, for example, is accurate. You can see all the readings are in the yellow region. All my throws are in the yellow region. So this is accurate, close to the actual target. Now this measures 20 kg, let's say, and all my readings 18.95, close to 19, 21.22, close to, you can see, 20, and this one as well, this is extremely close to 20. All of them are very close to 20. So all these readings are accurate. They are close to the actual attempt or actual target value. So this is the meaning of accuracy, how close your value is to the actual target. Precision is different. Precision means how close or how consistent your reading is. So how close your throws in this case are to each other. So for example, we can have a batsman in cricket who is very precise, very consistent, but they can be consistently bad. So nowadays, Babar Azam isn't doing well. So currently, over the last 1 year or so, or 2 years, he has been performing consistently bad. Although he's consistent, but the thing is, he's not consistently good anymore over the last 2 years. So you can have a low average. So for example, tail enders, the ones who bat at the end, they are consistently bad because they tend to score low scores, although they are consistent. So your consistency can be good or bad. Your consistency can be close to the actual target or far away from the target. So over here you can see my throws, all my three throws are very precise. Why? They are close to each other. So we just do a comparison whether they are close to each other. But the thing is, they are not accurate, because for them to be accurate, they should be in the yellow region. So they are precise but not accurate. Another example, so for example, over here we have 23.11, 23.09, 23.12. All of them are close to each other, so they are precise. But are they close to the actual target of 20? Not really. So they are not accurate, but they are precise, so they are close to each other. Okay, now a few examples over here. You see all my throws are in the yellow region, so they are accurate. Yes. Are they precise? Are they close to each other? Yes, they are. So this would be accurate as well as precise. Next example over here. Are my throws in the yellow region? Yes, they are accurate. But are they close to each other? Not really. You can see they are not very close to each other, so not precise. Accurate but not precise. Next, my all three throws are near each other, so they are actually precise. But are they close to the actual target, the bullseye, the yellow region? Not really. So they are precise but not accurate. Lastly, Over here you can see one of my throw is over here, the second one over here, third one over here. Only one of my three throws is on the target. So are they accurate? Not really. But and are they precise? Not really. They are far away from each other. So not accurate and not precise. So these are the concepts for the first chapter. And assalamu alaikum everyone, welcome to the class. So now we'll be focusing on um, the past paper questions of the first chapter of physics, length and time, or the chapter of physical quantities, measurements. The best practice here in all the past papers would be like you guys, once you look at the question, pause it, solve it on your own, and then you hear my explanation and then match your answers, so that you can actually know that how you performed. If you have studied the concepts, these should be straightforward for you now. The first question. Now, the diagram shows an enlarged drawing of an end of a meter rule. It is being used to measure the length of a small feather. What is the length of the feather? You can see this starts from this point and ends at this particular point. We always do ending point minus starting point, because this has a zero error. This is not starting from zero. So what we will go down from here, this is 30. You can see this would be 29. So this should be 29 minus, or 29 take away the starting point, which is 10. So this gives me 19. This gives me a reading of 19. And the unit over here, this is millimeter reading and this is centimeter reading. So this would be 19 millimeter. That makes A the correct answer. Now in centimeters, this would actually, I come down from here. For example, like this, I come down from here. This would be 1 in centimeters, and this would actually be somewhere around here 2.9. So 2.9 minus 1 is equal to 1.9 in centimeters, right? So that is why the rest of the answers are incorrect. A is the answer. A student wishes to find the volume of a small, irregularly shaped stone. So this is an irregularly shaped stone, irregular object. A ruler and a measuring cylinder containing some water are actually available. We have a ruler and a measuring cylinder. Which apparatus is needed for this? So because this is an irregularly shaped stone, we only need a measuring cylinder. We only need a measuring cylinder. We'll use a displacement of water. We don't really need a scale. We just need a measuring cylinder. So B has to be the correct answer. Okay, now this is non-examinable so far because we haven't done kinetic energy. Next, question number 4. A measuring cylinder is used to measure the volume of a quantity of water. Which measuring technique would not, this is emboldened as well, would not improve the accuracy of the measurement? So whichever improves the accuracy, we can actually cancel them out, because we are looking for not improves. First one, make sure the cylinder is vertical. Is this what we want? Yes, we do. Vertical improves our reading. The cylinder has to be vertical. This is what improves, so we'll cancel it out over here because we are looking for not improve. Make sure that the water surface is at eye level. Basically, avoid parallel accelerate. Do we do this? Yes, we do. This increases accuracy. So we are looking for not improve, so we'll cancel this out because this actually increases or improves our reading. Reading the top of the water meniscus. We actually take the reading at the bottom of the meniscus. That improves our reading. This would not improve our reading. Top of the meniscus. So this is the actual answer. Let's have a look at D as well. Using the smallest measuring cylinder available, yes, that would improve our accuracy. We are looking for not improve, so we'll cancel out D as well. The actual answer is C. Next, the diagram shows 4 identical spheres placed between 2 wooden blocks on a ruler. What is the diameter of one sphere? So there are multiple ways of solving this. So for example, I can take this reading, which is 12, and I can take this reading over here, which is 4. I can take the reading for 4 of these combined. 12 minus 4 would be equal to 8. Now I can just take 8 over here, and now because we this is the length of 4 of these spheres, so 8 divided by 4, this would actually give me 2 centimeters. So this would be the answer B. Another way of measuring this would have been just taking one of this measuring one of this sphere. So for example, this reading, this is 6, you can see, and the starting point is 4. So the difference between these two, just one of these, because they are looking for one sphere. So 6 minus 4 would also be 2 centimeters. So same answer. Okay, now a cook uh, wants to prepare some food and he needs it prepared by 1:15 p.m. It has to be cooked by this time. He uses an oven with an automatic timer that can be set to switch on and off at certain times. The oven needs to be switched on for 2 hours and 10 minutes exactly. And by 1:15 it should be fully prepared. At which time does the oven need to switch on? So this is not the starting time. This is when he needs the meal to be prepared, basically for eating and stuff. So the total preparation time is 2 hours and 10 minutes. So we need to go back 2 hours and 10 minutes starting from this. So when we go back 2 hours, so basically minus 2 hours, we'll get 11 and 15. 11:15, and it should be AM because this is 1:15 p.m. So we'll have 11:15 a.m. But we need to go back 10 more minutes. So because the preparation time is not only 2 hours, so I'll subtract 10 more minutes from this reading. When I subtract 10 more minutes from this reading, I get 11:05 a.m. This is when I need to start the oven. It has to switch on at this particular time. 11:05 a.m. A has to be the correct answer. Okay, now the diagram shows a measuring cylinder. Which quantity is used? Is this instrument used to measure? This is a measuring cylinder. It measures volume for me, right? Straightforward answer. Volume. D. Which option contains only the specified only? This is emboldened as well. Only apparatus that could be used to determine the volume of a small block of unknown material. So we have a block and we want to find its volume, of course. So either if it is a regular shape, we need the length measuring tool, and if it is an irregular shape, we need the measuring cylinder, right? But this is a block. A block can be in a cuboid shape or in a cube shape, so we can use meter rule for it as well. So we are looking for a meter rule and a measuring cylinder, so A has to be the correct answer. It has both options. And in B you can see stopwatch. Not really, we don't really need to measure time. In C, balance is used to measure mass, so don't really need it. Stopwatch, this measures time, not volume, so A has to be the correct answer. Next question. The diagram shows a measuring cylinder used to measure the volume of a small stone. What is the volume of the stone? So we just take the final reading. This would be my V2. You can see 20 over here. Each line is basically 2. So I'll have 22. This would be 24. This would be 26. Next would be 28 and then 30, right? So each line is actually 2. And I'm one line below 20. So this should actually be 18. I just need to do V2 minus V1. This is my V2 and this is my V1. So 26 minus 18, that should give me 8. So cubic centimeter, because you can see the unit over here, A has to be the correct answer. Next, a student uses measuring cylinder to measure the volume of a quantity of water. Which action would make her results less accurate? So whichever is more accurate, we can cancel it out and eventually we'll have less accurate left. Making sure her eye is level with the water surface, this would improve the reading. This would improve the reading. We are looking for less accurate, not more accurate. We'll cancel it out. Making sure the cylinder is vertical, this would improve the reading. We are looking for less accurate. Reading the bottom of the meniscus, yes, that is what we do. This will improve our reading. So we are looking for not improve or make a reading less accurate. Using the largest measuring cylinder possible, we use the smallest measuring cylinder possible for accuracy. This would actually make it less accurate. So D has to be the correct answer. Next, a student uses a measuring cylinder to measure the volume of the water. The diagram shows the part of the measuring cylinder. The top and bottom of the meniscus are labeled. What is the volume of the water? We always take the reading at the bottom of the meniscus. So basically, I need my reading at this particular point. So this should be my reading. So we can check from here. This is if this is 40, this line should be 41, 42, 43, 44, and the next one is 45, right? So every second line is basically equal to 1. So this particular line should be 46 and this line over here should be 47. So this, there is just a type over here. So let's say option A was 47 and option B, let's say, was 47.5 cubic centimeter. So we are just looking for 47 over here. Whichever option had 47, that is the answer that we choose. So in this case, A should be the answer. I hope this is clear. The actual reading is 47, so you just need to look for that option. Okay, now a student wishes to measure accurately the volume of approximately 40 cubic centimeter of water. She has two measuring cylinders, a larger one that can hold 100 cubic centimeter, a smaller one that can hold 50 cubic centimeter. The 41 can actually fit into this smaller one as well, because its maximum reading is this. The water forms a meniscus where it touches the glass. So, which cylinder would the student use, and what is the water level? So, for the most accuracy, we always use the bottom of the meniscus. So in terms of water level, either A or C is the correct answer. Top of the meniscus, this we won't take. So B and D is already out. Next up, we look for the cylinder. We use the smaller one because this is in the range. You can see 50 and it is approximately 40. So this is within this range. We use the smallest possible within that range to get the best answer. So we'll be using the smaller one. So C has to be the correct answer for question number 12. Next, the diagram shows part of a ruler. The ruler is used to find the length of a nail. Once again, we have zero error. What is the length of this particular nail? So we have zero error over here. This would be 3. This would be 3.5, 3.6, 3.7. So if I go down from here, this is actually 3.7. And the starting point you can see is 1, and this is in centimeters. It has been the unit has been given over here. So I just need to adjust for zero error. I'll go down from here. This was 1, of course. So this is my starting point, SP. This is my ending point. Ending point minus starting point is what I need to do to adjust for zero error. So this would be 3.7, take away 1, this would give me 2.7, and this should be in centimeters. So I'm just looking for 2.7, so B has to be the correct answer. Next, question number 15 over here. 14 was off topic. The diagram shows a measuring cylinder containing water. Five identical steel balls are now lowered into the measuring cylinder. The diagram shows the diagram 2 shows the new water level in the cylinder. What is the volume of each? This is important piece of information. Each steel ball. So I'll just call this V2. This is 70, and I'll call this V1. This is 40. So I just need to do V2 minus V1. So 70 minus 40. 70 minus 40. This should give me 30. Is this the final answer? Not really. This is for 5 of these steel balls. So I'll divide this by 5 and I'll get 6 cubic centimeter. This would be the volume of each of these balls. So A is the correct answer. A stopwatch is used to time a runner in a race. The diagrams show the stopwatch at the start and end of the race. How long did the runner take to finish the lap of the race? So this is 1/100th of the second. So basically, I can just take this starting point as 50.1, for example, and I need to convert this in minutes as well because this is in minutes. So but this is in seconds rather. So I'll just convert this in seconds as well. So we have 50.1 seconds over here. The unit have to be the same. Then we can add or subtract them. So 1 minute would actually have 60 seconds. So this is 60 plus 40, 100. So 100, and I have 10 over here as well as I had 10 over here. So 100.1 seconds. So I just need to do ending value minus starting value. That would adjust for zero error because this has zero error. The start of the lap was not from 0. The stopwatch did not start from 0. It actually started from 50.1 seconds. So 100.1 minus 50.1. This should give me 50.0 seconds. So I'm looking for this particular answer, which would be A. Next, the diagram shows the readings on a measuring cylinder before and after a small metal cube is added. So let's have a look at the diagram. It was initially 3, and after a metal cube is added, it rises to 5. So volume of one metal cube is basically 2. 5 minus 3. It is 5 minus 3 is equal to 2 cubic centimeter. This is for one metal cube. How many more they are saying? You need to read the question carefully. How many more? They specified more. How many more identical cubes can be added to the cylinder without causing the water level to overflow? Do not, they specified, do not include the cube that is already in this particular cylinder. We will not include that. So if I add one more, the reading would come to 7. If I add one more, if I add another after it, the reading would rise to 9. If I add one more, the reading would rise to 11 and it would overflow. So I can't add the next one. So I can only add two more for it to stay, for the water to stay in this particular measuring cylinder. So over here, I'm looking for 2 as the answer, B. Make sure you do not add the cylinder which is already, the cube which is already present. They specified. And they specified over here as well how many more identical cubes. So more would be after the first one. So the correct answer is B. A lot of students just write C without reading the question properly. Next, a student measures the length of a rod XY by holding it next to the meter rule. The student writes down the length as 94.8 centimeters. Which of these answers is correct? So first of all, this is my ending point. You can see this is 99, this is 95. So this X is my ending point, and 99, this would be 99.5. This is 99.7, and my starting point is this particular value. This is 2 behind 95. You can see I have 94 over here. So the this is my starting point. Y is actually 94.8. 94.8. So if I want to find uh, the length over here, I just need to do ending value minus starting value, final minus initial. Ending value is actually 99.7 minus the starting value is 94.8. This will give me the length of this particular object. I just need to do 99.7 minus 94.8 ending value minus starting value. So this would actually give me 4.9, and this should be in centimeters. It has been given over here. Now let's have a look at the options given to me. The value is correct. Is the length 94.8? Not really. It should be 4.9. A is out. The value is incorrect because it should be 95.2. No, it should be 4.9. So B is out as well. The value is incorrect because it should be in millimeters. No, they have given, specifically given centimeters over here. It should be in centimeters. In millimeters, it should be this value multiplied by 10. So basically 49 millimeters. So C is out as well. We definitely know that the correct answer is D, but we'll give it a read. The value is incorrect because the student should subtract the reading for end Y from the reading at end X. Yes, this is what we did, right? Final minus initial reading. So the correct answer is D. Next, a student uses a ruler to measure the length and width of a small rectangular metal plate. What is the area? They're looking for the area of this plate. Now, this is a cuboid shape. The area of a cuboid is actually a length times width. Length times width. So I'll first look for the length. So my both length and width, they have zero error. So over here you see my value is not starting from 0. It is actually starting behind 0, and this would be 2, 3, 4. Ends at 4, but I need to add this extra bit that I have, these two bars basically. I need to add this extra bit, and each of these bars is equal to zero point 0.1 basically. So I need to add 0.2 extra, this part extra. So from 0 to 4, this was definitely 4. I need to add 0.2 extra for it. So the length is actually 4.2 centimeters. Now let's have a look at the width. This is the starting point, 0.5, and 2, 3, 4. So 4 minus final minus initial basically. Final minus initial, because my reading is actually starting from a value that is ahead of 0. So final 4 minus 0.5, this would be 3.5. So 3.5, I'll just put it in this formula, length times width 4.2 times 3.5. Let me just put this in my calculator, and then we'll see what the actual answer is. 4.2 times 3.5, 14.7. So do we have an option with this? Yes, B is the correct answer. Next, a cyclist rides around a track 3 times. So this is important piece of data, 3 times. Her friend uses a stopwatch to record the time at the start of the ride. After one circuit, at the end of 3 circuits, the readings have been given. So at the start, we have 6 seconds, so zero error. After one circuit, this is the reading. After the end of 3 circuits, 600 seconds is the reading. So what is the average time? For average, what we need to do is take the reading of all 3 circuits combined and divided by the number of circuits, which would be 3. So I'll just use final minus initial to remove the zero error. So final reading would be 600 minus 6, 594 seconds. This is for 3 circuits. Circuits means 3 rounds basically. This is for 3 circuits. Now 594 divided by 3, this should actually give me 198 seconds. So this should be the answer. We cannot use one circuit value because for average we take total for all circuits combined, all laps combined minus the initial at the start if there is a zero error, and then divided by the number of laps. So the correct answer has to be C. Next question. A cylindrical can is rolled along the ruler shown in the diagram. The can rolls twice, so it is being rolled 2 times, rolled twice. What is the circumference of this particular object? And you can see after one roll, it reaches this particular point. So I'll take a common point. So if I take this as my common point, starting from 0, now for this particular, at this particular and this would be my common point, like the starting point of this particular circle. So this is basically 13. So 13 minus 0, 13 centimeters would be the answer. You can take other points as well. So for example, I could have taken this arrow point. This is starting from 2 now and ending at 15. You can see this ends at 15. You can see over here. So I can do final minus initial. 15 minus 2 is equal to 30 centimeters, right? You could have done, could have taken this value as well. This is 28, and then 28 minus the starting value, exact same point, would be 2. This gives me 26, but this is for 2 circumference, so I need to divide by 2. I get the same answer as 30. So A is the answer. Okay, now drop of water is dripping steadily from a tap. The diagram shows a measuring cylinder which has collected 120 drops. So for 4 cubic centimeters, I have 120 drops. So basically, if I just do 120 divided by the number of volume, basically per cubic centimeter, this should give me 30 drops. This is drops per cubic centimeter. Now, how many drops in total will have been collected when the measuring cylinder reads 10 cubic centimeters? So we just need to do, this is 30 drops per cubic centimeter. I need for 10 cubic centimeters. So 30 times 10 would be 300. So we are looking for 300 drops. That is given in D. You can use ratios for this as well. There are other methods to solve this question. Next, what is the length of the object? So over here we have 2, then this should be 3, 4, 5, 6, and this is 6.5. This is the ending point, final value, and this is the starting point, 2.5. Final minus initial, 6.5. 6.5 minus 2.5, it should give me 4 centimeters as the answer, and the answer should be B. Next question. The diameter of a copper wire is thought to be 0.3 millimeters. This is extremely small. What would we use? Micrometer screw gauge for this, because this length is extremely small. For less than 1 centimeter or less than 10 millimeters, we use micrometer screw gauge, right? Micrometer screw gauge. So C should be the answer. You can see the length is too small for us to use tape measure or meter rule or ruler. C is the answer. Which measurement can be made using a micrometer screw gauge? So micrometer screw gauge basically measures length for us. So air pressure in A, no. And in C, turning effect of force, no. Wavelength, no. This is not length of a wave. This we use a different tool for it. Uh, we can't use a length measuring tool basically to measure wavelength of microwaves. So for B, you can see diameter of a wire. This is the length. So B is the correct answer. Assalamu alaikum everyone. So in this class, we'll be doing the second worksheet of this chapter, length and time, or physical quantities measurements. So let us get started with these questions. We'll only do on-topic questions. Which set of quantities are all vectors? So they should have magnitude as well as direction. Acceleration, yes. Displacement, yes. Distance with a specific direction. Velocity, yes. Speed with a specific direction. So all of these are vectors. A is the correct answer. We'll see why others are incorrect. You can see this has mass, scalar quantity. Extension is just length, scalar quantity. Energy, scalar quantity. Question number 3. A student determines the circumference of a golf ball. Which instrument gives the reading that is the circumference of this golf ball? So for this particular question, basically you can see it would look like this. So we need a length measuring tool that measures this circumference for us. So it should be something that bends, and you can see tape measure is something that bends, right? We can't use vernier caliper or micrometer screw gauge. It can't measure circumference of, for us it can measure diameter if the length is small enough, and meter rule, it can't measure length for us either, because that is for straight objects. Question number 4. Which quantity is a vector quantity? Force. And a good example would be weight. Weight is a force as well, which has a direction vertically downwards. Energy, speed, time, all of them are scalar. Question number 5. Is mass a scalar or a vector quantity, and is acceleration a scalar or vector quantity? Mass is a scalar quantity. So we are looking for scalar, either A or B is the correct answer in terms of mass. So C and D is already out. Acceleration, this is a vector quantity. So the correct answer has to be B. Next, the diameter and length of a thin wire, approximately 50 centimeters in length, are measured as precisely as possible. What are the best instruments to measure this? Now, this is a thin wire, so we need to measure its diameter. So, for a thin wire, to measure its diameter, an appropriate tool would be micrometer screw gauge, because it can measure very small lengths, for example, thickness of a wire. And this specified thin wire, so it must be micrometer screw gauge. Next, around 50ish centimeters in length, either we can use a tape measure or a meter rule. So let's have a look at the options. For a thin wire diameter, it has to be micrometer, so we can just cancel out C and D already. And for length, we will be using rule, because 50 centimeter is in the appropriate range of a rule, 10 centimeters to 500 centimeters. So the correct answer has to be A. 1 year caliper can't be used. Maximum length it can measure is 10 centimeters. Of course, it can measure more than 10 as well, but for greater accuracy, up to 10 centimeters. 1 centimeters to 10 centimeters. Next question. Which quantity is a scalar quantity? So over here, the temperature is the scalar quantity. Acceleration, force, velocity, all are vector quantities. Scalar means only magnitude, no direction. Next, during an experiment to find the density of the stone, the formula for density is, I'll just write it down over here. Density is equal to mass over volume. Uh, to find density of a stone, the mass is lowered into a measuring cylinder partly filled with water. It is lowered in this because we need to find volume. You can see in the formula we need mass as well as volume. So which statement is correct? The difference between the two readings gives us density? No, it gives us the volume. The difference between the two readings gives us the volume? Yes. See, the final reading gives us the density? No. We actually need to take the volume from this. This would give us the volume, and then we need to take mass as well, then mass divided by volume to get density. C is out. The final reading gives us the volume of the stone? No. That would not be your volume of the stone. Basically, the final reading would be volume of the stone plus water. We need to subtract the water's volume, basically the initial volume, to get the volume of the stone. B is the correct answer. Next, the diagram shows a micrometer scale. Which reading is shown? So we have two parts. We have the main scale part. So let's take the main scale reading wherever it ends. If you look closely, there is a line over here. So this is 5, 6, 7, and there is a line after 7 as well at the bottom, 7.5. So this would be 7.5. This is the main scale reading, 7.5. Then we need this additional reading. You see this small line over here after this reading. We need this small reading as well. How do we find this reading? Wherever the datum line coincides with the thimble scale, that is the reading that we want. So you can see this is the 14th line over here. So I'll just make a line over here, 11, 12, 13, and this is 14th line. And to get the thimble scale reading, for thimble scale, we need to take this reading 14 and divide it by 100, because 100 of these lines are equal to 1 millimeter. That is the reason. So this would be 0.14, and both these are in millimeters. So final answer should be, we add these two together, 7.5, 7.5, and then we add 0.14, and that should give me the final answer, 7.64, and this should be in millimeters. So D has to be the correct answer. Next, which is a scalar quantity? Mass. Force, velocity, weight, all of these are vector quantities. A is the answer for this one. Next, what is the reading on the stopwatch? So you can see this is 30, this should be 35, and the next line, this should be 36. So we are looking for 36 seconds. So C is the correct answer. So far so easy, right? Okay. Each row contains a vector and a scalar quantity. In which row is the size of the vector equal to the size of the scalar? So displacement, its comparative scalar. Comparative scalar should be distance, because displacement is distance in a specific direction. So speed, although this is scalar and displacement is vector, the columns are correct, but they specified equal to the size of the scalar. They won't be equal in magnitude. Size means magnitude. So that is why A is out. Next option, velocity and distance. No, velocity is comparative scalar quantity, is actually speed. So although this is scalar and this is vector, but the thing is they won't have the same size. We need the same size, equal size, is specified equal size. So for C, you can see velocity over here and speed of the car. They would have the same magnitude, because speed is basically yeah, without direction, and velocity is speed with a specific direction. The magnitude can be same, so C is the answer. And for D, you can see this is weight, this is mass. Are they same? Not really. Weight is actually equal to mg, mass multiplied by gravitational field strength. Their size is not equal. So the correct answer has to be C. Question number 17. Which device can be used to measure thickness of a single sheet of paper? So we need a length measuring tool which measures the smallest possible length. Micrometer, screw gauge. The other length would be that is used to measure bigger lengths. So basically micrometer, less than 1 centimeter length, that would be the thickness of a sheet of paper. So micrometer would be the appropriate tool. A micrometer is used to measure the diameter of a uniform wire. What is done to get an accurate answer? Find the reading and add or subtract zero error. Yes, we need to adjust for the zero error. We can either add or subtract depending on whether it is, if it starts from a value greater than zero, then we subtract the initial value. If it starts before zero, from a value of less than zero, we actually need to add that particular value. So this is the correct answer. Let's see why other options are incorrect. Make the micrometer horizontal. That doesn't affect it. Whether it is vertical, horizontal, has no difference. Subtract the fixed scale reading with rotating scale. No, we add them together to get the final reading. Subtract the rotating scale from fixed. No, we add those to get the final answer. Is the correct answer. Before marking the finishing line on a running track, a groundsman measures out its 100 meter length. Which instrument is the most appropriate? We can't use a meter rule, because its appropriate range is 10 centimeter to 500 centimeters, and the maximum, this is actually equal to 5 meters only. This is equal to 5 meters only, and we have 100-meter length over here. Now B is out. and 30 centimeter ruler is too small. We can't use this either, and it would be appropriate for smaller readings. Micrometer, this is for less than 1 centimeter. Is the correct answer. Measuring tape can be up to uh, like starting from 0.1 meters, basically 10 centimeters, to 100 meters. It can be bigger than this as well. The tape should be big enough, and it is easy to store as well. In a small space, you can uh, store a measuring tape measuring 100 meters as well. So A was the answer for that question. Next question. Which pair of quantities includes one scalar and one vector quantities? In A, both are scalar quantities, mass and time. In B, both are scalar, temperature and time both are scalar. For C, temperature is scalar and velocity actually is vector. C is the correct answer. In D, velocity, weight both are vector quantities. So C is the answer. A reel of copper wire. Reel means a wire that makes like a coil, for example, like this, right? A reel of copper wire is labeled 30 length of 30 meters and diameter of 2 millimeters. This is less than 1 centimeter, right? 1 centimeter has 10 millimeters. A student calculates the volume of the copper wire. Which instruments does he use to measure accurately the length and the diameter of this particular wire? So for diameter, you can see micrometer screw gauge, less than 1 centimeter. The most accurate tool would be micrometer screw gauge. That way, either B or D is the correct answer. We can already cancel out A and C. For length, 30 meters. A tape measure can measure bigger lengths up to 100 meters, but a meter rule can measure lengths up to like 5-ish meters. So the appropriate answer would be tape measure for measuring length. That makes D the correct answer. Which row correctly shows examples of vector quantity and scalar? For vector, area no, mass no, velocity yes, and weight yes. Now for scalar, like A and B are already out. We'll just cancel them out directly. For C, this acceleration is actually a vector quantity, so we'll cancel it out. And D is the actual answer. Volume would be scalar. D is the answer. Which velocity is given by the change in displacement divided by change in time? How many vector quantities appear in this particular statement? So over here we have velocity, speed with a specific direction, vector quantity, displacement, length in a specific direction, vector quantity, and time is scalar. So you have two vector quantities. So C has to be the correct answer. The level of water in a measuring cylinder is 75 cubic centimeter. A stone of volume 20 cubic centimeter is lowered. Initially, this is your V1 basically. This is your V1. Now, a stone of volume 20 is lowered in it. So this is for water only, 75. What is the new reading? So basically, we already have 75, and then we add or we place a stone of volume 20 in it. So we need to add this. This would be the final reading. They are not asking us to find the volume of the stone. They have already given 20. So this would be my final reading with those two combined. So the correct answer has to be D, 95. The diameter and length of a thin wire, approximately 1 meter in length, are measured as accurately as possible. What are the best instruments? Thin wire. So because this is thin, so most likely this should be micrometer screw gauge to measure diameter over here. So either A or B is the correct answer. We can already cancel out C and D. Now for length, because this is 1 meter in length, vernier caliper can actually measure up to 10-ish centimeters, 1 centimeter to 10 centimeter. So B is out. So the correct answer is A. Although like these questions, they have vernier calipers because they were part of the previous syllabus, but not anymore. The quantity is quoted as having a value of 6.2 ms. If you remember, this m was for milli, and milli was actually 10 raised to power minus 3. If you remember, this was in the prefixes. Milli is 10 raised to power minus 3. Okay, now in what units is it measured? Is this measured? So you see S is for seconds. S is for seconds. So milliseconds is what we require. D is the answer. This is not meters. It should have had only M for it. Meters per second would be meter, then slash s, meters per second. Microsecond, micro actually has this symbol. This would be microsecond, and for milliseconds, ms. D is the answer. The following statements are about motion. Which statements describe vector quantities? A plane flies due east. This is direction. This is direction, right? And this is length in a specific direction. So this is a vector quantity. Uh, a runner's average speed. This would be scalar. Around the track, 5 meters per second. Speed is scalar. So this is out. A snail crawls 3 millimeters per second. This is speed in a straight line towards a lattice. This is the direction given. Speed with the direction is actually your velocity. So this would be my velocity. This would be my velocity. Okay, now this is velocity is also a vector quantity. A tourist travels 500 kilometers. This is just length. So this length is scalar. So 1 and 3 is what we are looking for. B has to be the correct answer. Power is measured in watts. What is the correct symbol for millions of watts? Million basically means mega. 10 raised to power 6. Million means mega. Uppercase M is the symbol for mega. And for watts, we use uppercase W. This is unit of power, which we'll do later on in our syllabus. So uppercase M and uppercase W. So correct answer has to be D. Okay, which list contains only scalar quantities? So acceleration is vector, A is out. We have force in B, this is out. Force in C, this is out. So we know the correct answer has to be D. Length, mass, speed, all are scalar quantities. Which statement about scalars and vectors is correct? A scalar has direction, not really. A scalar has only magnitude, no direction. A scalar has size, yes, and no direction, yes. So this is the correct statement. A vector has direction but no size. Size is magnitude. Vector has both direction and magnitude. C is out. A vector has size but no direction. It has both size as well as direction. So the correct answer has to be B. Which list contains only scalar quantities? Acceleration is vector, A is out. B also has acceleration, B is out. Displacement, length in a specific direction, C is out. D, distance, mass, speed, all are scalar quantities. The correct answer has to be D. What is the reading on this micrometer? So this would be 6, and you see this is my main scale reading. I'll just write m dot s for main scale, 6.5. This is my main scale reading, 6.5. Now thimble scale, I'll just write t dot s. So the datum line, or the line that this datum line is coinciding with which line? This is the 13 line. This is 10, 11, 12, and this is 13. So we take this reading 13 and divide by 100 always, because 100 of these are equal to 1 millimeter. This becomes 0.13. This becomes 0.13. Now the final answer should be these two combined, 6.5 plus 0.13. Okay, now I add these two together. So the final answer should be 6.63. This is what I'm looking for, and this should be in millimeters. So this is what I'm looking for. B is the correct answer. I hope this made sense. So for 43, the correct answer is B. Next. Which of the following correctly lists one scalar and one vector? The displacement is a vector quantity, so A is already out. Energy, this is a scalar quantity, yes, and force, vector quantity, yes. B is the answer. For C, you can see force has been written, which is actually a vector quantity. C is out, and velocity is also a vector quantity. It is written in the column of scalar, so this is out as well. In an experiment, a ball is rolled down a curved track that is that is about half a meter long. So half a meter is basically 50 centimeters. Which measuring device should be used to measure this length? You can see this is curved. For curved lengths, we use tape measure. For curved lengths, we always use tape measure. We can't use meter rule, although this is in the appropriate range. But the thing is, this is not a straight line. Meter rule is used for measuring straight lines. Micrometer is used for measuring lengths of less than 1 centimeter, not in the appropriate range. Similarly, vernier caliper less than 10 centimeter. Basically, 1 centimeter to 10 centimeter, not in the appropriate range either. The diagram shows one method of measuring the diameter of a beaker. What is the diameter of this particular beaker? Now you see we have been given wooden blocks. We just need the diameter of the beaker. So we will not include the wooden blocks. So this is its ending point. I'll go up from here. This is 2, 3, 4, 5, 6, 7, 8, 9. So 8 is my final reading. You can see this is the ending point, and the starting point actually is this point over here. This is my starting point of the beaker. I will not include the wooden block. They ask the diameter of the beaker only. So this is actually 3.5. So I just need to subtract these two, final minus initial, basically adjust for zero error, final minus initial reading. So this would be 8 minus 3.5. That gives me 4.5 in centimeters. We can see the unit has been given. So 4.5 A has to be the correct answer for this particular question. A student studies some equations. How many vector quantities are contained? So I'll mark the vector quantities. You see force, this is a vector quantity. Acceleration, this is a vector quantity. It has a direction, of course. Velocity is a vector quantity. Displacement is a vector quantity. Length with a specific direction. So we have marked 4 vector quantities. So that means the correct answer should be D. Which is correct statement about force and velocity? Both would be vector quantities. Force and velocity are both scalars? No. Force and velocity both are vectors? Yes, they are. Force is scalar? No, it is vector. Force is vector and velocity is scalar? No. Velocity is not scalar, it is vector. So B is the correct answer. Okay. Next, a student has been asked to determine as accurately as possible the volume of a piece of wire. The wire is about 80 centimeters long, so appropriate tool in terms of range only would be meter rule as well as tape measure, and about 0.2 centimeters in diameter. This is less than 1 centimeter. So micrometer screw gauge would be the most appropriate tool to measure the diameter, micrometer screw gauge. That being said, either A or D is the correct answer. It has micrometer. So we'll cancel out B and C already. Now, for measuring length, this is 80 centimeter, which is out of the range of vernier caliper. Maximum range for vernier caliper is 1 centimeter to 10 centimeters. So D is out. So the correct answer has to be A. Okay, so next question. Which of the following groups of physical quantities consists of only scalars? Acceleration in A is vector, acceleration in B as well, vector, force in C, vector, mass, speed, time, all are scalar. D is the correct answer. Now, last question of this worksheet. One oscillation of a swinging pendulum occurs when a bob moves from X to Y and back to X again. So one full round, one oscillation would be it going from X to Y and then from Y back to X. That would be one oscillation. Using a stopwatch, which would be the most accurate way to measure the time for one oscillation? Multiple readings concept. Time 20 oscillations and then multiplied by 20? No, time 20 oscillations divided by 20. So A is incorrect. B, time 20 oscillations and divided by 20. This is taking average, multiple readings and then dividing, so that the human reaction time is removed or at least decreased by many folds. C, time one oscillation, although this will give us the reading but not very accurately. We need as accurate as possible, the specified most accurate way. So C is out. D, time the motion from X to Y and double it. So this would be the least accurate. Over here, we are not even doing one oscillation. We are actually doing half oscillation. So this would be the least accurate. So the correct answer has to be B. This was the last question.